Okay, so let's see. I thought I would start today with this quote that I told you about before. This is from Feynman's lectures on physics, which are really excellent introductory books. Well, I guess I should say they're really excellent books. Most people find that they're not, for most people, suitable for introductory books. I think that was the experience they had when he taught the freshman physics class. But once you've had the course, the standard course, and then you come to read the Feynman lectures, there are a lot of insights there that are really good. I do think Rizzi's textbook is even more insightful. But this is interesting here because Feynman was concerned about trying to understand things and not simply having a set of equations. He really wanted to understand. He challenged himself to understand things. And in the volume on E&M, he expresses this. He's a little unhappy with writing a book, even after spending so many years learning physics and trying to understand physics. He says, "You might ask me to explain what is an electromagnetic field. I'm sorry, I can't do that for you. I don't know how. I have no picture of this electromagnetic field that is in any sense accurate. I have known about the electromagnetic field for a long time. I was in the same position 25 years ago that you are now, and I've had 25 years of experience thinking about these wiggling waves. I see some kind of vague, shadowy wiggling line." So what he's referring to there is when we get to chapter 6, we're going to study radiation and electromagnetic waves and get an antenna and set up an oscillating charge distribution on the antenna and send out a wave. Here and there is an E or a B written on them somehow, and when I talk about the field swishing through space, I have a terrible confusion between the symbols I use to describe the objects and the objects themselves. So he really sees that problem for himself, and he expresses the problem very well. I have a confusion between the symbols and the physical thing. What I realize now is that when I talk about the electromagnetic field in space, I see some kind of a superposition of all the diagrams which I've ever seen drawn about them. And I think he expresses the problem really well. I mean, so he goes on, in spite of this problem of not really understanding what he's doing, he goes on and teaches, the symbols and the equations and how to manipulate them, things like that. But he sees a deficiency in his own understanding. And this is what I think, it's very clear, that Dr. Rizzi's book really supplies, is what is lacking, even in such a well-respected book as Feynman's lectures on physics. That confusion between the symbols of the objects and the objects themselves. I think Dr. Rizzi does a very good job of helping to fix that. So here's another, let's see, this is in the book. I briefly talked about units before. This is in Appendix 6, page 21 of Appendix 6, so it's in the back of the E&M book. Relationships between the SI and CGS systems of units. So the SI involves meters, kilograms, seconds, so MKS plus the addition of the charge now. And so there are these different symbols that we have and the units that we use to describe the measurements. So there's a momentum is in viridans, for example. In joule, charge is measured in coulombs. And the scalar potential phi is measured in volts. And so those are the things we've encountered so far. The electric field would be measured in volts per meter. And and also then resistance down here at the bottom. Resistance is measured in ohms, and capacitance is measured in farads after Faraday. Okay. Now, and so these are the common units. You're used to saying volts, ohms, farads for those elements. So SI is a much more common system of units if you're dealing with, picking up elements, trying to build a circuit, go to Radio Shack, you want to find something that'll be measured in those kind of units. CGS units, as I said, they make the the equations tidier, they're simpler, but they're not as common. So momentum would be measured in phors, PHOR, and I've forgotten what 4 stands for, why that name. Force is in dynes, energy is in ergs. charge is measured in electrostatic units, ESU. The scalar potential is measured in ESU per centimeter or a stat volt. Electric field then is in stat volts per centimeter or ESU per centimeter squared. And let's see, resistance is in what is that? Is that S per centimeter? Is that stat volt per centimeter? And capacitance is even some other unit is actually in centimeters. Is that right? No, that's not cm. I'm not sure what that refers to. Okay, so they're quite different units. Okay, now if you have then a circuit which is an RC circuit which has a resistor measured in ohms of say 1 ohm, and this capacitance is in a farad, which is a hefty capacitance. It's pretty easy to find a 1 ohm resistor. A 1 farad capacitor is a pretty hefty capacitor. You make an RC circuit out of that. The time constant will be 1 second. Okay, so we're going to do that demonstration right here for you. So let's see here. I'm going to show you first the setup that I have here. And unfortunately, this document camera is off-center. It doesn't, and it won't let me zoom in. If it zooms in on this piece and not on the rest of this. But here we have a capacitor, a battery, and then just a resistor. This has several resistors that I could select from, and I've got one here. It's the smallest one on this board is 10 ohms. And I've got it rigged so the battery goes through the capacitor and through the resistor, and there's two switches. This switch is for the circuit with the battery, and this switch will close the circuit with just the resistor and the capacitor, no battery. So this is the charging switch, and this is the discharging switch. And then I have, in addition here, over the discharging switch, I have a current meter. It's also a voltage meter, but I can only do one at a time, so I've got it set on current right now, currently set on current. And so now I'm going to, so you don't see what's going on with the charging, unfortunately, with this setup. So I'm going to close the circuit here. And so what this is now going, the battery is now going through the resistor and the capacitor, and it's a 10 ohm resistor, a 1 farad capacitor. So what's the time constant? No, 10 ohm resistor. So it's 10 seconds. So it takes 10 seconds for it to get to 1 over E of the final charge. Okay, so I wait a few seconds for it to charge up. Okay, now that's charged. Okay, and so and now I'm going to discharge it here. So I'm going to switch over here to this computer that has a USB link here for this. This is an old plot, so don't pay attention to that. I'm going to redo this so you can see it. So this voltage, this current meter, ammeter, is connected into the computer through this USB link, and this thing is set up to display this. So now I'm going to push record. Oops. Okay, try it again. There's recording. See, okay, now it's going to wait for me to. I'm going to start the discharge. So as soon as I do the discharge here, there you can see now that's the current flowing through the switch through the circuit. Okay. So this is just the discharge part. Okay, and the scale down there at the bottom is a little hard for you to see. The scale all the way across is 30 seconds, so you can see a time constant of about 10 seconds. Looks about right. Okay, so now I'm going to stop that. I'm going to change resistors here. I'm going to up it to, let's see, 100 ohms. So the time constant ought to be what? 100 seconds should take a lot. But I need to charge up the capacitor here. Oh, I should have charged it first. Hang on. I'm going to charge it with the 10 ohm resistor. It's a little faster, and you can't see that anyway. So I'm going to charge that a little faster. Otherwise, I won't get as much charge on it. Okay. Now I'm going to switch resistors, and I'm going to do the discharge. I need to start to record here. There we go. Okay, now I'm going to do the discharge. Oh, I didn't charge this. I charge it up as well. Okay, and now the time scale, remember, is about 30 seconds there on the scale, the horizontal scale. And it's a little harder to see. I'm going to try to go back here. I'm going to get that charge doing better. Let's go back. Hope the battery's not dying on me. Kind of mixed the whole thing. Not work so good. All right, let's try it again. Switch over to the 100 volts. Okay. The 100 ohms. Didn't get as much. Oh, well, of course, there's less current. Of course. Of course. Stronger. Okay, let's see. I wonder if I can change the scale. I don't know how to use this so well, so I'm afraid of fiddling with this. I don't play with this as much. Okay, but you can see that the current is getting weaker. It's a little hard to see on that scale. I'm going to extend the scale here. And we said the time constant is 100, and it's starting to look like it's not a bad number, 100 seconds here. We've gotten up 40 seconds there. So the exponential decay looks quite clear. Good demonstration of that exponential function. And if I keep waiting, of course, it's going to go asymptotically to 0. So the capacitor will be completely discharged then, and so there's nothing driving the further current through the resistor. So the current will go to 0 asymptotically. Takes a long time to completely discharge that. Okay. All right, now let's see. Okay, so what is today, the 3rd? Okay, so in that demonstration, in the homework you were to write the circuit equation for the two circuits, one with the battery and one without. So the circuit equation is a differential equation governing, say, the charge on the capacitor. So the circuit with the battery has a battery voltage, and then it has oops, that's not a theta, it's a Q, should be Q dot plus Q over C. This is writing the circuit equation in terms of the charge on the capacitor. So that's the circuit equation with the battery. So this is the charging cycle. When you take the battery out, then you have, that is the circuit equation. So it's without the voltage. So that's what is referred to as the circuit equation. It's also called then the governing equation for the circuit. And we used the word governing equation when we were doing mechanics. We talked about the governing equation. So in that case, for example, we had a differential equation for the, say, the simple harmonic oscillator, right? Mx double dot was minus kx. So that's what we mean by the equation of motion for the governing equation. In the circuit equation, we have something mathematically of the same type there. It's a differential equation that holds for all time. And then so we have some initial conditions as well. So we have, in addition to the circuit equations, we have the initial conditions. What's the initial charge on the capacitor, for example? Okay, so that's what is meant by the circuit equation, the governing equation, and the equation of motion. Generically, it's some kind of differential equation. When we get to study inductors, we'll add inductors into this circuit, and we'll have a second order differential equation. That is, it'll be a Q double dot. So it will look more like the equations of motion that we're used to dealing with in mechanics. Okay. Okay, so now the schedule here for the next couple of days is this for Friday. You have homework due, and we'll we'll discuss that here. I'm going to set you up for doing the homework for Friday. Monday, you have a practice test I want you to finish doing and bring to class. I emailed that. Everybody should have gotten that by email. And we'll go over that in class. And then Wednesday, there's an in-class test. And the practice and this test, of course, cover chapters 1 and 2. So there's a study guide on Blackboard, and also there's the chapter summaries. Every chapter has a summary. So I suggest between the practice test, the study guide, and the chapter summaries that's a good way to prepare for the test on Wednesday. I think the midterm grades are due before or very close to when we're going to have our next test. So your midterm grade will consist of homework grade and this test. Okay. So we may get the next test will be after chapter 3, and we may get that in before I have to give you your midterm grades. Yes, sir.
Last semester, all the tests were cumulative.
Yes.
Are these the same way?
Yes.
Will it just be from this semester then?
Yes. Yeah, I won't count last semester on this semester grades. So everybody starts fresh slate. Let's see, now the weighting is a little different than last semester. I think I'd weight the finals more this semester than last time. I think that's right. I say that, but I need to check the syllabus. The weighting is a little different. So all of the chapter tests will be a fraction of the final grade, and the final is some fraction in the homework. And as before, the homework grade in principle, everybody can make 100% by doing a good job, a decent job on the homework, turning in a good effort. Okay, so now what we have. Let's go back over what we have here in the so far in electrostatics. We have Maxwell's first and third equations. We have them in two forms, integral and differential form. So the differential form describes the relationship of the divergence of the electric field at that location is related to the charge density at that location. So that shows clearly that the charge density is causing a divergence in the electric field. And the electric field will only diverge where there is charge. And that's, again, expressed in terms of this charge density. So this is the charge density here is a volume charge density. So amount of charge per unit volume. So if I have a small element, a small volume element, the amount of charge contained in that volume element is the charge density times that little volume. Okay, and so those are the differential and integral forms. And usually when you see Maxwell's equations written down in the 4 equations, you see the differential form. They contain the same information expressed in different ways, in a local form or in a more global form with the integral, because you're summing up the electric field, how it the flux through a surface in the integral form on the right. So the left-hand form, the differential form, describes what's happening just at this location. The Maxwell's third equation, which we haven't talked about much, is that the curl of the electric field is 0. This is in the electrostatic condition. That is, nobody moves, nothing's changing, or it changes very slowly. And so we'll modify these equations when we relax the electrostatic condition, which we will do progressively. And so the complete form of Maxwell's equations, the full thing, these will be slightly different, but they will involve the divergence in the curl of the electric field. And there's an integral form for it, but I won't talk about that right now. We're going to come back and study the curl in the next chapter, chapter 3. We'll come back and study the curl more both the definition of the curl and the theorem that goes with it, which is called Stokes Theorem, which plays the role of Gauss's theorem, but for the curl, where Gauss's theorem relates to divergence, Stokes theorem relates to curl. So we'll talk about that more in chapter 3. We'll come back and study that. But the content of it is that the electric field has no circulation. You don't see vortices in the electric field in the electrostatic case. If you have charges placed out and nobody's allowed to move, they're static charges, the electric field will not have any vortices, no circulation. And that's what that curl means. You'll only have diverging electric field. Okay, so now it's easy enough. If I have the electric, okay, now the next thing I want to describe also in terms of that, we also say that this equation here, not what I wanted, this equation here allows us to write an electrostatic potential. That is, the electric field is then can be expressed in terms of the electrostatic potential. And this is a lot like what we discovered with conservative forces. The conservative forces have a potential energy, which is a function of position. We can also describe the electrostatic case as having an electrostatic potential or a scalar potential phi, which is a function only of position. And there's a relationship then between the electric field and phi. And in fact, if I take that, this electric field related to phi and plug it into Maxwell's first equation, I then have this relationship. It's called the Laplacian. It's a pi. This is called Poissons Equation. And it introduces a new thing there, that del squared. The del squared is the divergence of the gradient. Right? Because you have the divergence of the electric field is the gradient of phi. So this is called the Laplacian operator. It's a second order operator. Gradient is first order, divergence is first order. You take the divergence of the gradient, you have a second order. And in Cartesian form, the Laplacian looks like the sum of the second derivatives. The Laplacian is a scalar operator. That is, in this equation here, the equation, Poissons equation, is a scalar equation. It's only got signs, a function on the left-hand side matches a function on the right-hand side. In this case, the functions are of location, or position. Okay, so the second derivative, the Laplacian of the electrostatic potential, then is related to the charge density. So that's another way of writing, again, Maxwell's equations, but explicitly in terms of the scalar potential rather than in terms of the electric field. Okay, so those two equations, those set of equations, if I have the electric field or if I have phi, I can find out what rho is. So in other words, given rho, other way around, given phi, I can determine rho by taking the negative Laplacian of phi. So if I know what the electrostatic potential looks like, I can tell you what charge density generated that electrostatic potential. And the same thing, if I have an electric field, I can tell you to take the divergence of that electric field, and that will give you the charge density. Now, but often we would like to go the other way around. Suppose we have the charge density. How do we find phi and E? And Maxwell's equations are not directly set up to do that. It doesn't help you so much. So what we need is how to find, given phi, given rho, how do we determine phi or E? How do we do this? Well, actually, we started with something like that. Remember, we had Coulomb's law, where we had just a single, very small body with charge on it, and we could find the electric field from that. So let's start with that, and we'll see how to construct the general case. So, in the case of, if I have the rho, which depends on position, and I'm going to put a prime here. So here's my origin here, and there's a body out here with some charge distributed around it. So that's the charge density describes how is the charge distributed And the location of a little piece of that charge, a little volume here, is given by r prime. And I want to know either phi or e out here. I want to know what those are. And that location is r. It's some other location. And so the distance here, this vector, script r, tells you how far that little packet of charge is from the place where you want to know the electric field. And remember, we have the superposition principle. So if I can determine what is the electric field generated by that little bit of charge, I can add that up from all the other little pieces of charge, add it all up, and superimpose it to get the total electric field, or the net electric field, or the net phi. Okay, so it's really pretty easy, and it's actually easier to start with phi because phi is a scalar. So the contribution here, the charge that's located here, remember, is going to be rho at that point times the volume, and I'm going to describe, remember, I'm going to use prime coordinates for where the charge is and unprimed coordinates for where you want to know the field. So the charge inside of that little cube is the charge density times the volume element. So the little bit that that contributes to phi, remember phi goes like the charge over the distance. So it's dq over the distance, which is the magnitude script r without a arrow over it is just the distance between charge and the point r. Okay, so that's the contribution that that little bit of charge makes to the phi at that location, and I want to add that up. It's a volume integral. And in fact, so I could rewrite this because a little bit of charge is the charge density times the volume element is that. So that's phi of r. And writing it more explicitly here, I have the charge at some location, and then I have the magnitude that separates the 2 points, and I want to integrate over the volume. So this is a volume integral. And that gives me the electrostatic potential due to any charge distribution. And this is, in fact, the inverse of Poissons equation. Poissons equation, remember, was Laplacian of phi is minus 4 pi rho. This you could think of as being the inverse. How do I solve for phi in terms of rho? This integral is the inverse of that Poissons equation. Okay, now we could do the same thing for the electric field, but the electric field, remember, now we have to have accounting for the direction involved. So it's a little bit more complicated. So now we have the charge, the little bit of charge, and the electric field is going to be r over r cubed, right? The strength goes like 1 over the square of the distance and in the direction of r. So this is also equal to r hat over r squared. But when you're doing the integral, it's easier to keep it in this form. So the electric field at r is then integral of dq, and it's a volume integral. Here, integral dq of r over r cubed, and that little bit of q, remember, is rho times the volume element, dv prime, r over r cubed. So we have r minus r prime over the magnitude of r minus r prime cubed dv prime here. So it's a little more complicated. You have to keep the directions because the electric field has a direction associated with it. Each piece gives you a direction. Okay, so that's the general form. That's in the textbook. You've read it. We just didn't talk about it in the lecture. This is described in the textbook, both of these forms. And this is the, you could think of as the inverse of Maxwell's first equation. How do I find the the inverse of that equation? Well, this integral form does that. Okay, now we're not going to do in this course any of these volume integrals, but we're going to do a simple case of this, so you can see how it works. And the simple case that I've chosen is a one-dimensional problem because you can do a one-dimensional integral. So we're going to convert this to a problem. We're going to have a charge Q spread out along a line of length L uniformly, and the charge density now is lambda, is a charge per unit length, right? So it's the total charge divided by the total length of the wire. And you're going to pick a point here right at the midpoint of this wire, of this line, a distance y above the middle, and you want to find phi and E there. Now you already know what the answer is. You remember the answer? We've done this. It's in your catalog. This is a cylindrical geometry. You could use Gauss's law to figure it out if you don't remember. But you remember how do phi and E go around this?
1 over the distance.
That's right. The electric field goes like 1 over the distance. So it points radially outward. It was 2 lambda over y hat, right? That should be what we will get. If this is the y, I'm going to call this x and y directions. Okay, that should be what you get. And phi is, let's see, is I recall, must be 2 there. Yeah, that's right. Okay, plus now there's a question we haven't dealt with here, and that is, just like the potential energy, the electrostatic potential has to be defined with respect to a reference point, and we haven't discussed the reference point in this. So that will actually come out of the calculation you're about to do. That reference point will come out of the calculation here because we're defining the reference point in this particular way here. Okay. So this is what we should get. And we're going to try to get these by constructing the integrals. And this is your homework for Friday. You're going to do the integral, but the integral is not a volume integral now. It's just along one dimension. So this is going to be pretty easy to do. Once you figure out how to set it up, then cranking through it should be straightforward. Okay, so how do we set this up? So we're going to follow the same prescription here. So we have, here's the line like this, and we're going to, let's start the origin here. So we're going to label a point along here at the x prime. Remember, the charge itself is at prime coordinates. So we have a little dx prime there, a little element of the charge. How much charge is it located there? Remember, we have the charge is distributed uniformly with this density, linear charge density over the line. So how much charge is located in that little dx prime?
Lambda dx prime.
Right, lambda dx prime. That's how much charge is located there. And if I'm looking up here at a point, a distance y above the middle, how much does that little dx prime, that little bit of charge, contribute to phi at that point? So it's the charge divided by the distance. So the charge is dq, and what is the distance between these 2 points?
Square root of y squared plus x squared.
X prime squared. Right. That's the hypotenuse. And so this would be lambda dx prime over square root of x prime squared plus y squared. Okay, now phi at y then is going to be this integral. And the integral goes from minus L over 2 to plus L over 2, because that's the ends of the line. In lambda, there is Q over L. So I want you to go through these steps. I'm doing quite a bit here for you, maybe too much, but I'll let you, well, I won't set up the electric field for you. I won't take you quite as far there. It's more complicated, but you'll see the basic idea. So there's an integral you have to do. And then you go to the tables and find what is the integral of that thing. Turns out to be a logarithm, and you will find this constant here. So you should find, in addition to the logarithmic part, the constant. But there's actually a little bit more to this than that, and that is you're going to be making a further approximation, and that is in order to get. You'll find the complete solution. You'll find the complete solution. You'll find this only in a certain limit. This is not the exact solution that you get, which you get from the integral. The integral gives you the exact solution. This is only the solution in a certain limit. Remember the conditions that we placed on it. What were the conditions?
Far from the ends.
Far from the ends and close to the line, which means that y has to be much less than L. Because if you get far out away from the wire is going to get smaller and smaller. If you get really far away from the wire, it should go like 1 over the distance from the wire squared. The electric field should go like 1 over distance squared. Not like 1 over the distance, but 1 over the distance squared. So this holds only for y much, much less than L. And so you're going to apply that approximation. This integral gives you the exact form. This gives you the exact form with not that restriction on it. So you'll have the exact form, but then you'll also show that the exact form in the case where y is much less than L, you'll find is the form that we had before. It gives what we found before. And you say Taylor series and y over L. It's actually not bad. It's pretty easy. You've got the same pieces that you've had before, but I actually spell out. I give you the Taylor series that you need, but it's actually one that you're familiar with. Okay, so 2 steps. Do the integral. That gives you the exact form, and then take the leading behavior in the Taylor series when y over L is very small, and that will give you back what we've been using here. You remember this argument, this form was only holding in that limit. We always put that condition on there because we made those assumptions about the nature of the electric field and how it was uniform and so forth. If you get far away from that wire, from that line, so let's suppose you're way up here, distance y is much bigger than L. If we make a Gaussian surface here, remember it was a cylinder that was concentric with the line. I should draw that a little better. Here's the line. The charge is here. Okay, we made the assumption that there was no flux out of the end caps. Well, there's definitely going to be flux, electric field flux, coming out of the end caps. And so that messes up our application of Gauss's law because we assumed that there was no flux out of the end caps. It's coming out the belt. Okay. And that was fine as long as y was in close. So in that case, we had a little cylinder concentric with the line, and then we could say there was no flux out of the end caps, and that's fine because you're far from the ends, and the electric field is only going straight outward. But if you don't have that condition, like you're really far from the line appears to be really short compared to y, then you get flux out of the end caps, you've got to modify your calculation. And so that's why the argument that we had before isn't going to hold, and unless y is much less than L. Okay, but you don't even have to worry about those arguments if you're going to do the integral. This integral allows you to do the whole thing without making those arguments. You just crank. You set it up and crank, right? That's the power of the imperiometric, is set it up and crank. Turn the crank, and you don't have to spend as much time trying to figure out the pieces, how that all works. More likely to get it right that way, especially without understanding the details. Okay, so now the electric field is a similar sort of thing. The electric field, I keep hitting the wrong thing there. Okay, now the electric field is going to be similar, but now you have again a little dx prime, but you're going to need to construct the vector from the charge to the point. So we have this vector, which is script r. Okay, so what is the vector if this is the origin of the coordinate system? What is the vector r prime? Where is that little piece in this coordinate system?
From the line to y.
I'm sorry?
From the line to y.
No, I'm going from here to the charge, this first piece, r prime. The prime, remember, locates the charge. Where's that little piece of charge?
dx for x prime.
Yeah, x prime, and in what direction x hat? Not negative. It goes, here's the origin. And this vector r prime just goes from the origin to that little lump of charge. And now r goes from the origin to where you want to know the field. So what is that in the Cartesian?
Y hat.
Y hat. Okay. So script r is then x prime, negative x prime. Oh, okay. In script r it comes out negative. Is that what you were maybe getting? Right. This is script r. Remember, is r minus r prime. So you get a negative x prime. Okay, so and then now the integral is, again, it's one-dimensional. It's not a volume integral, but you have a vector in there, and you can see coming back to this. There's the electric field. So you're going to do the one-dimensional version of this. So instead of rho, you're going to have lambda. It's a one-dimensional integral instead of a volume integral over x prime, but you've got script r over the magnitude of r, script r cubed. Okay, so you get another integral. Now you might be concerned you've got now something that you haven't encountered before. That is, you're going to have something that involves an integral that involves, you'll have something that involves x hat and something that involves y hat, and you'll be integrating over dx prime from minus L over 2 to L over 2. And you might think, well, what do I do about those unit vectors inside the integrand, right? We've encountered taking derivatives of Cartesian vectors with respect to time. What did we do in that case? For example, we had the position vector, which was a function of time dependent on the coordinates x, y, and z, which were functions of time. And we've done this. We've taken the derivative of this with respect to time. And what do we do in terms of the unit vectors? What happens to them?
They stay the same.
Yeah, they're constant. They don't change in time. They're invariant with respect to time. And so we were just able to write that just by taking the derivatives of the coordinates. And that's the nice thing about the Cartesian coordinate system. You don't have to worry about the unit vectors changing. You're going to come across other coordinate systems where the coordinate unit vectors are changing with respect to location, and so it makes it more complicated to take derivatives. You have to be more careful. But the Cartesian has the advantage, they're just constants, they don't change. Okay, so now, going back, keeping that in mind, in this integral, these are constants in the integral, which are just like constants in a sum. You can factor them out of the sum. So that piece involving x prime, the x prime can be factored out. And the same thing for the y hat piece can be factored out. So you just factor those separately, pull those out separately, do the integral for the x component, and then you'll have another integral, a different integral to do for the y component. Be different integrals. And then the end result here is you will have then the electric field, the result of that integral, and then have two components in x and y in principle. Okay. In actuality, the electric field, you can see by symmetry for this location, the electric field, looking at the electric field here above the midpoint of this line, which way should the electric field point?
In the y direction?
Yeah, in the y direction. We said that earlier, right? In the y direction. It should point in the y direction. Excuse me a second. Okay, should point in the y direction. So this integral should give 0. Okay, when you evaluate the limits. Okay, so here's a challenge problem. Do the same thing, but don't look for the electrostatic potential and the electric field only in the middle here. Let's go off a distance x from the center of the wire. So now I want to know phi of x and y and E of x and y. Not just in the middle anymore. Any point. Anywhere. Doesn't even have to be inside the wire here, inside the length, someplace close to the wire. Remember, this is completely general, so I could find the electric field way over here and the phi field way over here. So I have x and y. Okay, so the challenge problem is it's just a little bit more difficult integral. It's really not harder. It's not a lot harder. So here's the challenge. Those who want more challenge, I want you to try to find the electrostatic potential and the electric field at any other point over here, not just along the mid point. Okay, now this is, again, it's a completely general, this is the exact answer, no approximations except the electrostatic approximation. This line charge is not moving. Okay, given that, and it's not, no charges are moving around inside the line. So, given that, this is completely general. Setting up that integral will give you the electrostatic potential and the electric field anywhere, and you can use that to find, for example, you should be able to verify, given that E is the negative gradient of phi. That should also work. And that works up here previously as well, just along the midline there. Yes, sir?
Does that still assume y and x are much less than the length?
No, it doesn't.
Okay.
Right,
Thanks
this is
for taking
completely
that
general.
up.
That no longer suffers from that. So you will have the exact answer for any place. So this should, if you get far away from this line, the electric field and the phi will start looking like a point charge, right? The total charge is on a line, but it's very small compared to the distance. So in that limit, you should recover what you would expect for a point source. And it will give the fringing field and everything. You could determine how the field fringes here around the ends. Right? We talked about how it should fringe. The electric field will come out like this. They don't curve. There we go. You'll get all that. And the only thing that you need to do here is to modify this R here. You would just now add x hat to that. Should do that in the same color. Okay, so for this problem here, in this general case, R is equal to x hat plus y hat. This is the piece you didn't have before. So now when you set it up and do the integral, you should get the completely general answer. So give that a try. It's pretty fun to do. And of course, you said x is 0. You should get back to the answer you get before. Okay, questions? All right, so we'll see you on Friday.
Figure out your hours.
Oh, make sure everybody, if you want to chime in on the hour time, I think only about half the class has responded. I want to make sure everybody, maybe a little bit more than half the class, I want to make sure everybody has responded, has a chance to respond who wants to. So let me give you that reminder. Please do that today. Then I'll set office hours. It's looking like they're going to change. That was good for you.
I mean, I might still shop it.
Yeah.
There at that time.
Right. Yes, sir.
The other day you mentioned something about a Faraday cage. That kind of
Yeah.
had a Faraday cage.
Yeah.
Did you ever work with it before?
No, I never did. Yeah. I don't think I've ever been inside one.
I was just wondering about it.
I don't think it's there anymore. It was in